In this example that we ended with at the end, you see a bundle which is designed for the agent. It has a name written in blue, which we decide for ourselves. It hides details, including variables, lists. It installs packages by talking to the local package manager and interfacing with that. It corrects bugs in certain environments. We see the green classes that allow us to pinpoint where and when, in what framework, in what environment, certain promises will be kept. And it allows us to integrate all of these things into a harmonious sort of automated structure that can be stuffed into the walls out of sight. I mentioned at the beginning that configuration management to a large extent is about knowledge management, and I think the future of configuration management is increasingly towards this division between what humans do and what machines do. And what's left for humans is to manage the knowledge. As our systems grow in size and complexity, the understanding of the system, just to be able to comprehend what it is we've created, that is one of the biggest problems that I see people have to solve today. So we've looked through some of these examples of basic low-level promises, and hopefully they're fairly readable at some level, but still there's the question of how do we read these promises? What knowledge do they bring to the process of managing IT systems? So there are these four questions: what, when, where, why. The what is the thing making the promise. The first, this affected object, this first thing in the promise, that's what is being affected. When and where, that's these classes, these green classes. We also, excuse me, in this, here we go, in this command embedding example, we saw when and where in this cron-like execution example. These classes will tell us when and where certain promises should be kept. This allows us now to talk about the things in an environment and to partition or categorize, classify this environment into regions, groups, environments, which don't have to be separate. They can be overlapping, it's no problem. We can talk about Solaris machines that are used by the computer science department. It's two overlapping categories. We can talk about the Linux machines that are in both computer science and chemistry. That's another category. We can combine these categories in any kind of way that we want to divide patches that we manage in different ways according to different requirements. So we know what, when, and where. These things are fairly straightforward. But the question that's always been missing from configuration management tools and from IT management software, I believe, is why. Why did we make this choice? Why did we add this user to etc password? Why did we set up this service? Why did we patch the link to the socket address to make it work? Who did that and why was it done? And in this world where people are changing jobs quite rapidly as well and moving from organization to organization, that kind of knowledge easily gets lost. The person who did it probably left last year. No one left understands why this was done anymore. So this kind of documentation is quite important to do. And people have tried to do this kind of documentation with documents, with wikis. These things don't work very well because it's very hard to maintain these documents. Unless documents are continuously being used and updated and read, they don't get updated. But part of my commitment to writing CFEngine 3 was to find a simpler way to build knowledge about a configuration, about a system that would be simple for technicians to write, to maintain. No one likes writing pages of A4 about the system. Nobody even really likes writing articles in a wiki. But comments are okay. We can just about do comments, right? So at the level of comments, I think we can start to use the technology of configuration to and the intelligence of the system itself to put together a documentation based entirely on comments. And that is one of the ideas we've had in redesigning CFEngine 3. So if we look at the generic structure of the CFEngine language, one promise, it looks something like this, and here are all of the bits and pieces. So every promise exists within a bundle. A bundle is a container, like a subroutine. It's natural to give a bundle a name, just as you give a subroutine a name, saying what it does, what it's about, what's going on. We may or may not choose to give it parameters to emphasize certain things that are being changed or information that's flowing back and forth, much in the way of common programming. So we have a container, way of containing things and classifying things, bringing things together. Then we have, of course, the promise type with a single colon, things like files, processes, commands, storage, packages. That's the type of promise we're making, the kind of thing we're talking about. Then we have where and when, the context in which this promise is made and being kept. And then we have the promise itself, as you've seen some examples of. And the thing I haven't mentioned is these comments, the traditional hash comments, like in Shell and Perl and other languages you're familiar with. These are normal comments. You can make these kinds of comments in CFEngine. But there is another kind of comment in CFEngine which we add as part of the language itself. The second line of this promise here, comment, arrow, the intention. Now these hash comments are pretty much addressed only to the people who are reading this code. So business people, for instance, wouldn't ever look at this. Manager kind of people would never look at this. But if when people maybe even responding on the help desk to errors and tasks that come up in error logs would never see these comments. But if we encode the comments about these promises in the promise itself, in the code itself, then these comments can follow the life cycle of this promise throughout the history of the machine. Which means that if something goes wrong with this promise, an error occurs in a log. This comment can be added to the log to explain exactly what the purpose of this promise was when the error occurred. It used to be that we would find, back in the early days of CFEngine, you would look through syslog and you would see, XYZ : danger, error, something blew up, and you wouldn't have any idea where this message came from, what it was talking about, what thing was being referred to. But now we would see, with this approach, we would see bang, exclamation mark, something blew up. This occurred as part of a promise in bundle with a certain name and a certain line number, and the comment was, the intention was, we were trying to execute a script which is a third-party application. And so by adding this little comment, we understand where we now have to look for this error, what is the origin of this thing that appeared magically in syslog. And we can actually begin to trace the source of the problem. The people working on the help desk don't know what's in the CFEngine policy necessarily, but they can now contact someone to whom this promise was being made. Notice promiser, arrow, promisee. The thing making the promise, a file, storage, whatever, the person or people to whom the promise is being made, we can add documentation here to say who is interested in this promise being kept. Well, it might be the business manager, it might be the Oracle group, or the database management group, or the web services team. We can simply add this documentation to the comment so that when that error occurs, it says in the log file, this person is likely to be interested in this information. This is the background for it. So you don't just get the error message, you actually have something to work with. That, I believe, is the kind of knowledge management that can easily be added by a fairly dumb system like CFEngine. By dumb, I mean not intelligent. It's repeating standard methods all the time, but with the smallest amount of effort, adding a comment, that information can come back to us in a good way when we need it. So we instrument every promise with comments, names to refer to this promise, promisees, who is interested in the outcome of this promise. It could be a person, an email address. It could be the name of another promise, which depends on this promise. And we can start to connect together things with track dependencies between certain rules and have CFEngine manage those dependencies. And then when we have in our commercial product, we actually can print nice pictures about these things and have reports that business people can browse and see that, this promise is actually addressing this business goal. And I see that this has had a few failures in the recent past, but it's 99% kept. And so things are doing pretty well. And you can start to evaluate the whole process of IT management from a business point of view. And this is actually something that will bring value to businesses and make it easier to manage those issues. Do you have a question? So the question is, when we add these dependencies, document these dependencies, perhaps pointing to different promises, can CFEngine then order these things in a particular way to make sure that dependencies are solved before the other promise? This particular mechanism is not used for that. It might be used for that in the future. That hasn't happened yet. For now, it's only used for documentation. And the reason for that is that, excuse me, sometimes when you chain things together in terms of dependencies, there isn't actually anything that has to be done. There's no action that's required to make this dependence work. It's simply a point of documentation about a relationship to something that may even happen somewhere else on a different machine. It may not be possible to directly invoke that prerequisite and have it executed. So because CFEngine is a distributed system, these dependencies could in principle be anywhere in the network, and it requires a greater sort of orchestration problem to make that happen. So to some extent, we may be able to do things with that in the future. At the moment, there's a different mechanism for making prerequisites happen, which we'll come back to. So you start to see the way that we can take information that's added very easily by a technical person, just by adding a comment, and a good comment. So sometimes when people add comments, also in version control, you see this. People, add a line to the code, and then the comment they type is line added to code, which is kind of obvious because if you do a diff or if you compare these things, you see that was what was done. More interesting is why you added this line to the code. We did it because it fixes this bug, or because a new person started and we had to register him in the database. All kinds of reasons for doing things. You really want to say why. So it's this why question that we try to address with these comments. And now at least we have a way of collecting and tracing this information as it goes through the system. So in fact, when you run CFEngine and you see changes being made, you will see as part of the output lines prefixed with an I colon, meaning information. I colon lines are information that contain the comment, the line number in the file, the location of the promise that resulted in this message. And this allows us to trace that information in an interesting way. So here's an example. Bless you. Here's an example of this killing the SNMPD daemon. Why would we want to do that? Well, make sure SNMP is not active by default. That's kind of a dumb comment. That's not a good comment. The why would probably be SNMP daemon has many security issues. Probably nobody changed the community string. So that would be a much more useful explanation to people looking at this saying, wow, what's wrong with SNMPD? Gives you a reason. And that will explain to people why this policy is being made and would probably prevent them from changing it back to something broken later. So knowledge. These comments, they appear in log messages, allowing us to trace them. In CFEngine Nova, the commercial product and upwards, these get turned into a relational map, a knowledge map, that allows you to trace, actually do diagnostics, trace problems to root cause and so on. They allow us to see relationships in the code itself. Even for the casual browser looking through the source code, it's good. It allows you to see what's going on in an easier way. And it also enables us to do some kind of impact analysis when we see which things depend on other things. So if I change this promise and I know somebody else is depending on this, then I know it can probably affect people down the line. So this now gives me some kind of indication as to what will be the impact of this change that I have to make. By adding these promisees, who's interested, we get to see who are the stakeholders in this promise, and we learn something about the human organization surrounding this configuration problem. So again, human part, machine part, keep them separate, but try to give each piece the information it needs to do the best possible job. And we tie this knowledge about policy to other institutional documentation. We can do that using CFNO, which is a new component in CFEngine, which allows us to create semantic web documents, tying the policy to other bits of documentation, online documentations, wikis, whatever you like. So, I claim that CFEngine gives a fairly simple way of managing systems. But what does simple mean? Everything is simple when you know how, and everything is usually pretty hard until then. So far, let's say that this is artificially simple. We haven't really shown any unique improvements in management, except that we have this idea of self-healing. We have something that can be brought back to a state that we know and is reliable and has been designed to have a particular state. We know we can bring the system back into this state and it will be reliable. But what happens when you have to manage a large number of these kinds of things? The complexity of size is one of the biggest problems we have to deal with in management today. Not least because data centers are growing. They're just, the biggest data centers in the world are huge. The largest customers using CFEngine are people with tens of thousands of machines running a single configuration on tens of thousands of machines. To be able to scale up to those sizes, you need not only good client-server connections, but you need to be able to understand what's going on in these tens of thousands of machines. And that doesn't mean oversimplifying it, like making all machines the same. That's too simple. Then you are limiting the humans who are using the machine instead of enabling them to do more with the technology. Alvin Toffler is one of my favorite people I like to quote. In the 1960s, he wrote this quote that the purpose of automation, the purpose of technology is not to mass produce things so that everything is the same. The purpose of technology is to enable it, to make it cheap, to make variations. So just as we have many different kinds of clothing that we can use today because we have efficient manufacturing processes, so we should have many different kinds of computers for different purposes because it's cheap to build machines if we have good technology for it. That's the way to think about this. But to be able to handle that, we need to be able to simplify the problem to its necessary and sufficient level of complexity. And the way we do that is to use patterns. We identify patterns that need to be reproduced. And in CFEngine, we identify patterns in lots of different ways. In the olden days, it used to be just classes. So you could talk about classes of machines, all Solaris machines, all AIX machines, all Linux machines. Or you could create a group, all machines in the physics group or in the computing group. All machines belonging to one customer or another customer. These are simple patterns. Another kind of pattern is a list of things, like a group is a list of things, yeah. Other kinds of patterns are certain files with certain names. all kinds of ways we can see patterns, and this is what humans are good at. Identifying patterns is what human beings are very good at. So we're now in the domain of what humans can do for this configuration management problem, not what the machine can do. We look for patterns because patterns compress information. The basis of all information compression, or data compression, of course, is to look for a thing that gets repeated many times and replace it with something smaller. This is what zip does. In the same way, when we're writing a configuration, instead of taking the same rule or the same promise and repeating it 20 times for 20 different objects, we should have that rule once applied to the pattern of those 20 different objects. And then we have much less information to deal with. The information has become compressed, it's easier to understand, and it's also more efficient to evaluate. So we're now looking to create simplicity by identifying patterns. And this, again, is a part of the knowledge management strategy. Of management. So what does pattern mean? Well, something that models something with many actual cases, an expression. A symbolic expression, perhaps, like a regular expression is a number of characters that models a number of matching strings. A list is a kind of enumerated pattern. A list of things is just a number of things that belong together. That's one kind of pattern. It's very simple. Lists are really good because everyone knows what a list is, from shopping lists to what have you. And I think one of the most successful things in CFEngine 3 is the way lists can be used to reuse bits of code to apply to many different objects. Regular expressions, of course, can be used to search through things like file names or files for strings, so search, replace, identify files matching a certain pattern, all .exe files, for instance, or files belonging to a certain etc directories on many different devices. All kinds of different patterns that get reused in operating systems, naming conventions. We can use these as patterns to simplify the process of management. And then the classes of machines, again, Solaris, Linux, AIX, machines belonging to a group. These kinds of these kinds of patterns allow us to paint a picture of the network configuration in a way that is easy to understand, because it's using a high-level concept like a pattern, and it makes it really quite efficient in terms of the amount of information you have to maintain. Just a quick comment. Classes in CFEngine are not object-oriented classes. I said recently at a talk I gave, object orientation is one of the most damaging things ever to have entered computer science. You may or may not agree with my statement. I can explain it to you afterwards. But this idea of classes as being hierarchies of things built on other things with inheritance and so on, this is not the concept of classes in CFEngine. Classes are merely a classification of a category of things that belong together. So here we are, classes, when and where. Classes are in fact just sets. Sets, all we think about is sets. Sets of things are just lists, basically, lists of items that we can use and refer to. And of course we can form unions of sets, we can form intersections of sets in order to refine a search or extend a search. So when we combine things using sets, we have all of the flexibility we need. And all of those object-oriented classes can be created using sets. The way sets or classes enter into CFEngine language is we have a promise type, files, processes, and so on. And then the class expression comes afterwards with 2 colons after it. And I'll try to write these things in green so that you can see them. And then comes the rest of the promise, the affected object, and all of the values and attributes that should be set for this affected object. So this is where we add to every promise a scope, if you like, an environment or a scope in which this promise applies, a context in which this promise applies. How do we know what these classes are? Well, when CFEngine wakes up, when you start the agent, it wakes up and says, where am I? What is my environment? What kind of machine am I running on? What can I discover about here and now where I'm running? And it categorizes all of this information in a long list, which looks something like this. If you run CFEngine -v, you will see this list appear quite early on. So every machine, anywhere, anytime, any place, anywhere, will define the class any. That's the wild card, it's always defined. Then some of the classes, like the green classes, are about the time. When did the agent wake up? So we see, in this example, the agent was started on Sunday at 8 o'clock in the morning. It was about 32 minutes past 8, in fact. More interestingly, 32 minutes is a bit too specific for most policy writers, but say between 30 and 35 minutes past the hour is a good way of representing that, because CFEngine generally runs, or by default it runs every 5 minutes. So in each 5-minute interval, we might be interested in having something happen. Q3 means that we're in the third quarter past the hour. So hour 8 underscore Q3 means, again, the third quarter past the hour of 8. It's the 21st of June. It was 2009. Life cycle 2 means we are in machine life cycle's second year. A life cycle is 3 years for a machine, according to this model. And then we have the time in GMT as well, which is useful if you're doing global coordination. If you have data centers around the world and you need to coordinate things in universal time, not local time, then we can use GMT time. Some of the classes refer to the way in which CFEngine is being executed. So the second one, verbose mode, tells us that we are currently in verbose mode. That means that certain things, you may want to report on certain things only when you're running in verbose mode, for instance. Then come a whole bunch of discovery classes about the kernel version, the system version, Linux, x86, 64, 266, 27, 23, SMP, this, that. Compiled on Linux, local hosts. Every machine is localhost, of course. The network interface is available on the system. The IP addresses being currently used on the system, both in IPv4 and IPv6. The particular version of CFEngine we happen to be running, this is a SUSE Linux, LSB compliant. It appears to be SUSE 11.1, and so on and so on. And this list of attributes or discovered attributes of the system will grow for as many things that can be discovered about the system as possible. We can use any one of these, combine them in multiple ways to create a context for a promise by adding it like this in terms of these green classifiers. So again, promise type, files, processes, storage, whatever. The class, which can be anything you like, either from this list, or we can also create things based on this list. And then the promise follows. So in class 1 or class 2, we do promise 2. On Linux machines at 2 o'clock in the morning, or on Solaris machines, we do promise 3. It sounds like a strange kind of thing to do, but who knows? People have all kinds of strange requirements in their environments. And we want to give them the flexibility to be able to model those strange requirements that they have. We can create our own classes by aliasing existing ones, or by creating further tests that we base on the environment. We can probe the environment for certain things and base things on that. To do that, we have classes promises. Classes promises are in a category of their own with a single colon. And then, for example, the first promise here says that my class, which is just the name of a new class, promises to be the OR of these two classes in this list, Solaris or Linux. So I could have written this actually in a different way, as you see at the bottom here, as an expression with the vertical bar to be an OR instead. I could have written my class expression Linux bar Solaris. That would have been the same thing. But actually, in some cases, it's useful to be able to use lists for these things, as some functions return lists. So let's skip the second one for a moment and go to the third one. We can create a class from an expression. Well, let's do the bottom one first. Sum promises to be a class set by the expression Linux and 2 o'clock in the morning or Solaris. It's the same one as we had here, except that here we use a dot, and here we use the curly ampersand character for and. You can choose which one you like best. Both mean and. Completely equivalent. And then CFEngine will evaluate this expression. If it's true, sum will become true. If it's false, sum will be false. If we look at the third one, this is an interesting one because this now combines the idea of classes as a pattern with regular expressions as patterns. So the third promise says, summary promises to be a class representing the expression, and now we have a special function, class match, web.star. What the class match function does is it goes through all this list of classes that have been discovered and sees if any one of them matches this pattern, web.star. If they do, then summary will be defined. This is useful if you use naming conventions in your environment. For example, some people have web servers and they call them Web 01, Web 02, Web 03, and so on, up to however many web servers they have. In that case, you can combine all of those web server class, all of those machines that are web servers, you can combine in a single summary class and refer to that instead by modeling that pattern using the regular expression. So again, it's all about looking to see what sources of information you have, what patterns exist in those sources of information, and finding ways to reduce the complexity of that information down to something manageable, talking about summary instead of a long list. Of course, we could equally well say Web 01 or Web 02 or Web 03 and list the whole thing with colon at the end of it. But it's much easier to create an alias summary like this. The second of these examples is an interesting thing. It was originally an experimental idea, but it was used quite a lot by users of CFEngine 2, where this used to be called strategies, inspired by game theory, where you can actually set classes randomly from a set. So you have a number of alternatives that should be defined with certain frequency. So this distribution is what dist stands for. Distribution class says that 10% of the time, let's see, do these things add up to 100? Yes, they do. Thank goodness for that. So these numbers add up to 100. So 10 out of 100 is 10% of the time. 20 out of 100 is 20% of the time. 10% of the time, you will get a class called my_dist_10. 20% of the time, you will get my_dist_20. But it will be a random selection, which allows us to make a random choice, flip a coin, do a load balancing, whatever it might be, for making a random choice. This is possible using these classes. And you see that when CFEngine executes at runtime, these classes that we've defined get evaluated, in this case locally within a particular bundle, and then they get added to the list of defined classes like so. So in this random case, we saw, this is obviously one of those 10% of the times that my_dist_10 got defined. And then all of these other classes undefined normally underneath. So many, many ways to model patterns on the system and to identify promises within a specific context that matches your environment. Combining classes, they really look just like Boolean variables, although this is an interesting point. They're not really Boolean variables. They are attributes that have been verified about the system. And they can be combined in expressions using the usual Boolean operators, not, and, dot, or ampersand for and, or can be one or two, actually as many vertical bars as you like. CFEngine doesn't really care. And of course you can put parentheses around things. I say these things are not Boolean variables because a class is only defined if it was possible to evaluate the right-hand side of this test. If we base a class on a test, let's say executing a script, and we find that script doesn't exist, but I've made a promise to say my class is based on the outcome of this shell command that I wrote, and oops, the shell command isn't there. Then CFEngine can't evaluate this shell command. It doesn't know if the outcome of this is true or false. It's actually an error. And an error cannot be represented in true or false. So it's not strictly a Boolean variable, but that thing won't be defined unless the thing you are trying to test, the thing you are trying to probe, can be observed. This is something we learn about huge systems in complex environments. You can't actually find out all of the information you need necessarily. Sometimes you won't be able to, and you just have to live with that lack of knowledge. You simply have to live with that uncertainty and cope with it. So you define your policy in such a way that it is robust to that lack of information you have about your environment. That's a strange idea, and I think we're not going to talk about it more today, but I'm happy to talk about it with you afterwards. I think this is one thing that people really have to understand about the difference between programming and designing infrastructure. We have to live with an uncertain environment. We do not control the environment in the same way you do in a computer program. And therefore, we have to be able to make things that are robust to all kinds of inputs. It's like input validation in programming as well. You don't know what the user is going to type. They can type any kind of rubbish. We have to be able to deal with it. In the case of this, the environment itself, the very environment we are working in, is the input to this program. So we need to deal with that. Regular expressions. Regular expressions can be used in many contexts in CFEngine. They're quite hard, I think. Regular expressions are tricky. But they are the standard way of matching free floating strings without some sort of embedded grammar surrounding them. To match a string fragment, a regular expression is the best way to do it. And in CFEngine we use Perl-compatible regular expressions because Perl has quite a nice model of regular expressions that is more powerful than the standard POSIX model. And people know it. People know Perl. So we decided to just standardize on this in CFEngine 3. I think creating your own regular expressions is hard. Always test them very carefully because these things are complicated. And better maybe to choose from a menu of simple cases. So pick a few patterns in regular expressions that you use and use again, things you know work in certain situations, and use them rather than trying to reinvent these expressions from scratch because you can make mistakes. And don't get more fancy than you know you can handle by yourself. Remember, the point about writing patterns is to make something simpler. So I have a friend who's a black belt regular expression master, and he has all these backslashes and commas and stars and ranges and all kinds of stuff with special modifiers that he knows how to do. And a normal person looks at this and says, what on earth does this mean? And I have to go and look in a book and spend half an hour trying to figure it out. That's not good communication. That's not good policy writing because the person reading this document should be able to see what it is that is the intention here going on. So try to keep things simple, because the point about a policy-based language, a declarative language, is that it speaks to the people looking at it in a simple way. We're trying to explain ourselves, not cover our tracks. So use of regular expressions, very powerful, a little bit dangerous, a little bit controversial, but the capabilities are there to be able to make really powerful things. And of course, because we can create interfaces and hide stuff, we can test regular expressions and hide them in bodies and parts of promises where we don't have to look at them. So experts have tested these things, and then users don't have to see them. Here are some examples of regular expressions, of course, just to remind you. Who's a regular expression expert? One black belt, and the rest of you sort of feeble-minded people like me who struggle to grasp the concept of these things. Okay, good. So the dot matches any character. Backslash dot escapes things. Backslash escapes things. Character ranges can be matched within square brackets like so. There's a number of backslash characters in Perl compatible expressions. Backslash s is a space, for example. Plus means more than one of the previous character. So backslash s plus would be at least one white space character. Backslash s star would mean 0 or more characters, and so on and so on. You can look these things up. So here's an example of how we might use a regular expression in CFEngine policy. There are probably hundreds of files that begin with etc pass on the system. I know one at least, the password file. And this promise says, look at every file matching this pattern and make sure that it has mode owner 644 root, these permissions. So if we have etc password, this will have these permissions. etc pass dog will have these permissions. etc password dot backup would have these permissions. Anything that matches this regular expression, anything starting with pass in the etc directory would be promised to have these permissions. Lists are another easy way of dealing with system management, and I think lists are good because we've all learned how to do shopping lists and things, but the other thing is access control lists are a paradigm that we use in management. Things we want to happen and things we don't want to happen. Things that are allowed and things that are denied. This is a simple model of allowing things. And so we find it easy to think in terms of these lists. And a list, of course, is almost also like a loop. We can iterate over all of the elements in the list and repeat something for each item in a list. So it's like a for each loop whenever we have a list. Now in CFEngine, lists are defined by these promises called as variables. In fact, we define lists as variables. We'll see that in a second. And then we refer to these lists either with a curly at symbol, meaning the entire list, or with a $scalar reference symbol for a scalar from the list. And if we ask for a scalar from a list, what we mean is each scalar item from the list in turn. And there is therefore an implicit iteration over this. What this says is essentially for each value in list variable, apply this promise to that value. So CFEngine can use lists and can expand these lists in fairly complicated ways and allow us to use patterns now to simplify the problem. So let's just look at how we define these lists for completeness. Variables promises are a kind of promise. This first line here says, the string scalar promises to be a string that contains the value scalar values. In a programming language, you would say scalar equals scalar values. In CFEngine, it's a promise, like everything is a promise. The second one is a list. So the second one says list var is an identifier that is of type slist, list of strings. And it contains, or it represents these values on the right-hand side, 1, 2, and curly at other list is a reference to other list. Other list is defined after this as the S list containing 3 and 4. So list var is, of course, a list containing how many elements? 4. Because it contains 1, 2, and 3, 4 from the other. And CFEngine is smart enough to be able to realize that the second thing was defined after the first thing, but because it has this convergent, self-healing approach to promises, it will follow this reference and evaluate, expand these variables accordingly. Now when we try to execute this commands promise at the end, a command saying bin echo hello $list variable, this is really 4 promises, not 1. It's equivalent to saying for each value in list var, bin echo hello $value. So this is automatically and transparently expanded into 4 promises saying hello 1, hello 2, hello 3, and hello 4. This is how we do lists in CFEngine. And it's nice to just get rid of all the for each syntax, which is irrelevant to the content of this thing, and understand that whenever we see a scalar reference to a list variable, that means it's a loop. How does this help us? Well, here's an example. This is a small fragment of one of many files that you'll probably recognize as being part of the Apache web server configuration. Apache, for some reason, has files strewn over the system in all kinds of different locations. And in one of those files, in one subdirectory buried within that file, completely obscured by comments, is this line in red that I've emphasized here for your attention, which contains a list of modules to be loaded by this server. Now, if I want to set up, say, a PHP server or a Java server as part of this web server, then I need to be able to add those modules to the Apache web daemon. And I do that by adding them to this list. Now, even if I am a super black belt system administrator that knows Apache, knows where to find this file in the first place, because I've done it many times before, finding this thing, firing up your editor, and finding this line amongst the forest of comments, and then editing this line, and restarting the server, it's going to take you 5-10 minutes to do that on one machine. Now you've got 200, 500, 1,000 machines. It's not going to happen. So we need a way of automating this procedure. Wouldn't it be nice if we could simply say, we'll use our access control list kind of approach and say, here is a list of modules that I want to have. These are things I want to be added. And here's a list of modules that I don't want to have, things I want to be deleted. And then we paste in a little bit of library code from the standard library to edit that line in that file and code this as a promise. And then all we're really doing is managing the data. We've separated the data from the rule, the promise that we're managing, and we have a nice clean separation. We're just managing the lists now. If one of these modules in the add modules list doesn't exist, CFEngine will add it. Just as it added users to the groups file. It won't add it more than once. It won't add it twice. It will add it once and once only. If somebody added it by hand, then it won't add it again. If somebody removes one by hand, it will add it back. Similarly, anything in the delete list, if it's there initially, will be deleted. You can't delete it more than once, of course, so that's convergent. But if somebody puts it in by hand, CFEngine will see that it's there again and it will remove it again. So we can continuously check that the correct number of modules are present at all times and have that managed by hand. And then, of course, we can arrange for, if this file gets edited, for CFEngine to restart the server to make sure that the new configuration is loaded. So this whole process can be automated, just as I showed you in the little film clip this morning of the Apache web server example. So this is the kind of approach we can use to simplify the management of something where lists of resources are required. We're making the same kind of promise, please add me to this line, to a whole list of things. So we use the list abstraction to be able to make it simpler, make it more efficient. In the same way, we can apply this to users, like we already did. So, of course, adding users to the system is quite easy. Removing users from the system is a lot harder because people tend to leave stuff all over the place. It's not just the home directory. Maybe they have cron jobs, they have @ jobs, they have files in /temp, they have email, they have all kinds of spooled directories. All of these things need to be cleaned up. So we can simply create a method, a standard method, an interface that takes the name of a user as an argument, and we can apply all of these rules to clean up or to add a user to each person in this list. And then, of course, we simply manage the list of users that we want, the list of users that we don't want, those people who've got fired or passed away or whatever happened to them. The system will maintain the system in the state in this state. It will manage these lists. Virtual machines, same idea. Anytime we have a pattern that we want to replace, install an image, give it a name, iterate over this list, create a bunch of things looking rather similar. If they're similar, then we don't need to describe them more than once, so we just iterate over the list. So this idea of using lists in CFEngine, I think, is one of the most important strategies for simplifying the problem, being able to clearly see the separation between data and method, and being able to hide information or reveal information at the right level, to make the choice about how to communicate in a most transparent way what it is that's going on in the system. Knowledge management. Anyone have any questions about lists and patterns so far? We're going to look at some more examples a bit later on, but I think this is a key concept in CFEngine, the ability to simplify things by using models. Model-oriented configuration is the expression these days, I think. Well, let's step back a moment. So I mentioned right back at the beginning that everything in CFEngine is defined in terms of a bundle. Every promise is made within some sort of bundle, and a bundle is a container. And then I've been talking a lot about these things in blue, these user-defined words, these templates that you can define for the system. But I haven't said how these things get defined yet. So let's just look at that. There are really two block structures within the CFEngine language, and they're called bundles and they're called bodies. A bundle is a container that contains a number of promises. A promise is a thing that describes something about the system that we would like to be true. And within the promise, you have the thing that makes the promise, the affected object, this first thing, we call it the promiser, the thing making the promise. You may have some promisees, things, stakeholders, people who are interested in the promise. And then we had everything else, which we call the body of the promise, what the promise is about. Just like we have the body of a document or the body of a contract. It's what the thing is about, the contents. Like in HTML, you have begin body and end body tags, for instance. Everything between those tags, the body of the document. Well, the body of a promise is a list of attributes that is described using something like this. And we can break up that list of attributes into smaller parts because the number of things we may want to explain in a promise is so huge. For example, I mentioned copying a file. To copy a file, you have to say where the file is, what kind of method you're going to copy it, using it from, what happens if the file already exists, should we keep a backup, are we allowed to use IPv4, IPv6, should we force overwriting the file if there's an object in the way, should we move other objects out of the way if they prevent us from copying the file, like 100 different things to decide about just copying a file. It would become completely unreadable if we tried to put all of those details in to the language description of this object. So we don't want to do that. In the old CFEngine, right back at the beginning, we used to put everything in one big long list. And trust me, it got very hard to read. So now we separate these things into parts, categories. You've seen permissions already. We've seen a couple of other things. So we had perms, colon. And notice, therefore, that there is a matching thing called perms, which allows us to define what objects of type perms. So we had MOG for mode owner group. We had MO for just mode and owner. Well, we would define one of those things by saying body perms MOG with some parameters. And then we would collect all of the details of that thing here in this body part. So we have three things. Bundles that contain promises. Promises inside them can be formed from body parts. Parts of the promise body can be separated out into little subroutine-like templates that can be reused and put into a library, a template library, like this COPBL, Common Community Promise Body Library. We declare these things like so. So bundle, agent, CFEngine words, my name, user-defined word, curly braces, and then a number of promises grouped together under the name my name. Similarly, body perms, CFEngine words, your name, user-defined word, curly brackets, and then a list of attribute settings, mode, arrow, value, left-hand side, arrow, right-hand side. As many of these things as we care to stuff into one of these bodies, this now becomes a template that we can refer to in the main code, if you like. So here's an example of how we can actually call a bundle of promises as a subroutine within another bundle. I mentioned the bundle sequence right back at the beginning. The bundle sequence is like a master list, a master schedule that tells CFEngine where to start. And if you like, that list can contain just one item, main, which is the main subroutine, and then you can call every other method in your CFEngine configuration as if it were a subroutine of main. You can do that if you want. This is how you would do that. So we would create bundle agent, some name, maybe it's main, called it my name here. And then we have methods promise within that bundle. A methods promise is a promise to use another bundle as a method. What that allows us to do is to call up a bundle called your name with certain arguments. So we can reuse that bundle for multiple purposes. For example, we're installing a user. We have an install user bundle or a remove user bundle. Just give the name of the user as an argument, and we can reuse that to do a whole bunch of related promises connected to removing or adding a user. Similarly with the virtual machine case. So we can package promises into useful, reusable bundles. And then, of course, allows us to say in which class, in which environment, in which context that bundle will be executed. So let's say in the class Monday, we have one set of bundles we want to use. On Tuesday, we have a different set of bundles. Or on Linux, one set of bundles. On Solaris, another set of bundles. So we can modularize our code according to time, operating system type, space, anything we like. Any kind of model can be created to cover these things. Does that make some kind of sense? Bundles within bundles, just like subroutines. So how do we link these things together? Well, we have the bundle sequence, which was in this part I mentioned, body, common, control. And this is a body part because there are promises within CFEngine that haven't been defined. They're sort of hard-coded into the software itself. Everything that's called a body in CFEngine refers to a promise somewhere else. And anything that's called a control body refers to control things that are built into the software. So, for example, the fact that CFEngine starts looking for a bundle and will execute bundles in a certain list, that's hard-coded into the software. It's kind of a promise. CFEngine promises that every time it starts, it will look for this bundle and start executing it. So yes, it's a promise, but this is something that explains the body of that promise. It explains exactly what is going to happen. So this is the body of control promises that are built into the software itself. And it's of type common because this applies to all of the parts of CFEngine, the agent, the server, the monitor daemon. If this had said body agent control, this would be promises just about the behavior of the agent, or body server control just about the behavior of the server, and so on. But here, each CFEngine policy begins with a body common control and a bundle sequence. It can be hidden from view, but it has to be there. And then, of course, we just have to define those bundles that are referred to, my name, and then we can connect up other bundles inside this thing as subroutines of this. And then it becomes essentially a list of bundles, each bundle containing a list of promises, each promise containing possibly a number of body parts, referring to different aspects of the promise. So, speaking of patterns, you start to see now a pattern of behavior that CFEngine has in the syntax itself. In fact, everything has one simple pattern, this promise pattern. The syntax has exactly the same structure for every single statement in CFEngine 3, whether it's a variable declaration, a class definition, a file setting, an editing command, jobs to be scheduled, a package to be installed. All of these things have exactly the same form because they're all promises. And the pattern we see going on is we have these red words, the CFEngine words, the blue words, which are user-defined words that you can change. We have in the declarations these two concepts of body and bundle. We have, as you see here, body and bundle. We have a second part of the name, which is agent, server, common, something like this. That's saying which part of configuration or which part of the software is going to interpret this. Who cares about this result? So bundles for agent are interpreted by the agent, kept by the agent. Bundles for the server are kept by the server. And then, of course, what's its name? What's the name of this thing, which is part of the knowledge management? It's how we group things together, and it's how we give them a meaningful name that we can understand. And then similarly with body, we have body, the type of body, what's it for, permissions, signals, and then what's its name? What are we trying to say with this template? So everything has this common structure, and once you've typed it out a couple of times, it's very easy to know. You expect it, and it's easy to apply. But let's go back a little bit to the software. We talked about the language, but CFEngine, of course, is a collection of programs. These programs are agents, components that interact with each other. Each agent runs on a particular machine. The agents run actually on every machine in the network that's going to be managed. And none of these machines is special a priori. There is no centralized server in CFEngine unless you want one. If you want one, you can have one. If you don't want one, you don't have to. Everything is open and configurable and free. CFEngine is an agent-based system, so the programs run on the machine itself. It's not, there are management systems that use, for example, SSH to log in on a machine and start manipulating commands directly by sort of like a remote control approach. It's not one of those systems. They're called agentless systems. CFEngine is an agent-based system, which means the software is installed on each machine and everything is handled by that agent on that machine. That makes it quite robust to loss of network, for instance. If the network goes away, CFEngine will continue to run. It doesn't break just because the network gets broken. Now, back in 1993, that was a design decision that I made because the Ethernet was quite unreliable in 1993. We used to have these coaxial cables that got pulled out of the wall, and or they got like the television aerials, and they got pulled out of the wall, and the cables would break, and it was quite fragile. That's no longer a problem. We have much better Ethernet now, but now we have wireless, which breaks all the time. And so the technology's changed, but the problems remain the same. And basically, we need systems that are robust to failure of transport technology and so on. We have many users of CFEngine in the Navy, at shipping companies who are out at sea, where when they're in port, maybe they have 2 megabits between themselves and the port, but when they're out at sea, it's like 2 kilobits, and then when the submarine's under the water, they have 0. So they still need to be able to operate when they're not in connection with their management centers of management. So agents are good because they can go anywhere, be anywhere, and adapt to their local environment. They don't need to talk too much with each other, only on a need-to-know basis. So it's very robust to have an agent-based system. That means we need client bits and server bits, though, to talk when we need to. And so there are multiple binaries involved with CFEngine. We can, because there's no particular model, we can deal with any kind of network model that you like. Everyone likes the centralized management thing to begin with until it becomes a bottleneck. So when you've got more than a couple hundred machines, centralization doesn't seem so fun anymore. Actually, you can scale CFEngine up to about, I think people have said, maybe up to 5,000 machines on a single server, which seems ambitious to me, but some people like to stress test these things. Probably when you've got 5,000 things, you want to split it up before then, just for the question of knowledge management, just to understand the model. But okay, fine, you can create peer-to-peer models, you can create centralized models, you can set it up exactly how you like. Every machine can be standalone if you want. You don't have to have any kind of client-server things at all. So this is fine, this is flexible. It means that CFEngine will work on or offline, with or without a network. And the other part about CFEngine is that it tries to be self-contained, have very few dependencies, third-party requisites, so we don't need a whole bunch of libraries to be installed to make it work. And if you download packages, in fact, from CFEngine website, all of the dependencies are included in the package in a special CFEngine working cache, so that even if you upgrade some of the dependencies on your system, CFEngine will continue to work. Even if you break the rest of your system, CFEngine can continue to work. So this robustness, this independence of independency, is a feature of the design of CFEngine because it has to work in environments that could be broken. Here are some of the components. There's an agent, which is the dangerous part, the part that makes changes, the active part, I should say. CF server daemon is the server, which can pass on files, deliver files. CF monitor daemon can do some basic monitoring. The exec daemon can do execution. It's a scheduling agent. And then you notice in brackets we have the old CFEngine 2 words. From CFEngine 2, it used to be called the same thing. Key invention in CFEngine 3 is what we call hyphen technology, which was introducing these hyphens. It actually allows version 2 and version 3 to coexist. So you can run both 2 and 3 alongside each other if you want to. And then these things in red are in fact new in version 3. CF promises is a preprocessor which allows you to check the syntax of your code before you execute it, find errors. You can find conflicts between different promise rules. So it can detect if you've made multiple promises about the same object which disagree, then CFEngine can pick up on this because the model was designed in this way to be able to find these things easily. CF report is a reporting tool which allows you to generate reports in text, HTML, XML for exporting to other software. In the commercial version, we have this reporting engine which goes on top of this, which allows reports to be gathered very efficiently as well. CFKnow is part of the integrated knowledge management. This allows you to generate semantic webs, actually, again using promises, to represent information and tie documents to configuration, and in general create a web of related information built on this knowledge that you add to the configuration underway. So it can use all sorts of processing tools and can end up with a sort of a set of web pages that allow you to browse the information in the network and integrate this whole thing into one nice picture. And then there's a run agent, CF run agent, should be a small c, which allows you to essentially simulate a push. CFEngine is a pull-based system. You cannot force a remote system to do something it doesn't want to do. But using the run agent, you can ask politely another machine if it's willing to pull a new configuration or accept information voluntarily. So this gives us a way of effecting immediate changes or to cope with special situations on a sort of a one-off basis. Basically, it's just part of the suite of tools that gives you the flexibility to manage changes as you like. The normal way of using CFEngine, of course, is that the agent wakes up every 5 minutes. It looks at the model of policy that it has. It tries to compare the current state to its current model. If it deviates from the model, it fixes it, brings it back into compliance with the model. But every now and again, you may want to make a change that is only something you want to do once because it's, I don't know, maybe you want to shut down all your systems, for instance, because there's a power cut. Then CF run agent might be the kind of thing you would use to make that one-off kind of change to the system. Here are the components depicted on two machines. So on the left-hand side, we have one machine. On the right-hand side, we have another machine. The agent, again, is the active part, the thing that makes any changes. And it cooperates with the exec daemon, the top, which schedules when the daemon will be run. So exec daemon runs a little bit like cron, except that its only purpose is to execute CFEngine, collect any output that comes from CFEngine, and send it to the sysadmin by email. And the default behavior is that exec daemon wakes up CFEngine every 5 minutes. The monitor daemon can run alongside. It's optional. You don't have to run it. And it feeds information to the agent about the environment. So it can monitor things like the number of users, the number of processes, number of connections to the system. And if this thing grows to a certain level, becomes a problem, then that information will be fed to the agent. The agent can respond to that information. So policy can be made dynamical based on the current state of the system, not only what's on the disk, but what happens to be running, what happens to be connecting to the network. The true dynamical state of the system is part of the environment. The server can feed files to the agent or the run agent. So the run agent and the agent can communicate with a remote server in order to download files if it's been allowed, if it has access. No system has access by default, but we can set up this kind of communication if necessary. And so we have a client-server possibility. We can create schemes in which the clients and the servers on machines talk to each other, share information, possibly centralize information, but not necessarily. And each machine has an agent running on itself which is responsible for its own state. And that independence from outside influence, I think, is a key thing to CFEngine, and that flexibility to be able to set up communications between client and server is also an important flexibility in the way that CFEngine works. So here's the policy architecture, if you like. Every machine can be standalone if you want. My laptop is a standalone machine. It runs CFEngine. On my laptop, for instance, I have rules that take a backup of my file. They take a backup to the same disk. What's the point of that? Well, the reason you take a backup, of course, is to protect against the threat of loss of data. Guess who is the greatest threat to loss of data on my laptop? If I should count the number of times I've been traveling and I've managed to delete some files by mistake, it's quite easy on Unix, rm-r. A carefully misplaced space between a star and a word can delete far more than you expected. These are problems. So, configuration management has uses even where you least expect it, even on embedded devices, protecting against me. So machines can be standalone or they can be tied into a network. People have, locked down data centers with highly efficient networks. People have sparse networks with highly unreliable networks, like the Navy. This is normal. Centralization is a useful tool in management because it allows us to bring consistency. A single point of change brings consistency to management. But a single point of failure is the downside of that. If that one place becomes unavailable, then you may have sabotaged the entire system from a single point. I remember walking around, let's say, a large search engine in the 90s. Not the one you're thinking of, but another one. And I walked around their data center because they were using CFEngine. They wanted to show me this. And we walked past this point on the network and said, see this cable here? This is our single point of failure. If you pull out this Ethernet connection, the whole thing goes down. So use centralization wisely. Single point of definition, great, but one thing that CFEngine does reasonably well is it caches information it needs on each local machine. So you may centralize information if you want, but then it gets downloaded to a local directory on a local system so that each machine will continue to function even if the network becomes unavailable. It's very important. By the same token, push is not allowed in CFEngine. These old systems, this sandblasting approach to configuration management, where you basically fire a bunch of software at the machine and hope for the best. That doesn't work, of course, if the network is down or if the machine is down. You cannot send information, and then you don't necessarily know if the machine got updated or not. But in an environment where machines may or may not be up or down, it's far better for the machine itself to take responsibility for its state, because then at least when it wakes up, it can repair itself. according to its own convenience. So pool-based management is much easier to adapt to dynamical environments, unreliable environments and frameworks. So there is no push in CFEngine. It is explicitly disallowed, both because it's not a very good model for updating, and B, because it's a possible security threat. I usually ridicule management by push by saying it's actually indistinguishable from an attack on the system. You know, firing a bunch of software at the system, you may as well be attacking the system. Much better for the machine to decide when it's convenient, what it wants to collect, what it needs, rather than having someone from the outside being able to do that. Then, having created this system where the end machines, these green nodes, are responsible for their own state, but allowing for the possibility of a single point of definition, this blue blob at the top, we can imagine creating some kind of architecture for running CFEngine in which we make our changes at the blue point, the policy definition point, which is done in conjunction with some sort of version control system so that we can track changes and intentions and so on. And then for scalability, that we publish these policy definitions on a number of yellow distribution servers that make available policy in a scalable, load-balanced way. You know, maybe you do this by country. So you have one server in the Netherlands, you have one in the UK, you have one in the US, wherever your data centers are. Maybe you have several in the same data center because the data center is very big. Doesn't matter, you can decide. It's up to you. But ultimately, it's these end hosts, these green hosts. Oh, and maybe, by the way, these yellow hosts are green hosts as well. They're just playing the role of distribution servers. But each one of these machines is looking after itself and has cached the information from this policy definition point so that if we now cut through these connections, these wires, all of those green and yellow machines will continue to work and be protected. You might say, if the network goes down, then who could possibly log onto those machines and attack them or break them? We still have the keyboard. We shouldn't forget the keyboard. And there might be back channels, multiple network interfaces, of course. Many ways to kill a cat, as they say. I think it's almost time to break for lunch, but when we come back, I want to explore this point about client-server communications in some detail and explain how to set it up and how the access control works, how the security model works. Clearly, the security model is an important part of a management system where you're giving essentially the power of root to some software.